an NCG, that's a new college grad, will probably be hired for, or what are the options or openings that you'll be having, and then what it takes to compete, right? So what it takes to compete to get into a graduate opening, then what is technical knowledge you need, how or where you can get them, what are the practical options you have once you graduate to get into the semiconductor industry. There are multiple ways in which you can get in, so I will just briefly touching upon that, and then we can have a small Q&A session after that. So what is VLSI, right? So to sum it up, I can just show you two photos that would actually sum up what VLSI is. So what you see on the left is the first digital computer that was ever created. And that was, I think, in mid 1900s. And what you see on the right is the latest Snapdragon Qualcomm 865. If you see the left one is extremely huge. It fills up the room, and you probably might be thinking like that is like maybe 100 times more powerful than the one on the right. But it's actually the exact opposite. The chip on the right, that's Qualcomm's, at least a million times more powerful than the first computer that was ever made. And the form factor in which that Qualcomm chip sits, it's hardly like a 1 centimeter across a single die. So that's what VLSI is mainly about. It's about, packing complex circuitry into as much small form factor as possible, creating complex circuitries which can fit into your mobiles, you can fit into your computers, into various machines with billions and billions of transistors. So where do we use this? So it's easy to explain what VLSI is, but it's most of the people only know about this as computer processors, but there is the use case of this industry is beyond that. So I would just like to show you very brief a glimpse of what is the potential of the semiconductor industry in the world right now. So I guess that gives you guys, at least a small idea about, what hardware can do, right? So almost everything that you saw is powered by a GPU or a high computing processor. So VLSI industry is spanned across. You can see VLSI or semiconductors in computers and mobile processors. You can see it in computer graphics for gaming. So that's another billion-dollar industry. It's there in content and media creation. Almost all Hollywood movies right now are created on GPUs for compute and rendering. You would see it in biomedical applications. The era of bringing out scans and manually reviewing it is almost going to die soon. You're going to have AI compute cancer. You're going to have AI predict a disease. You're going to have AI scan yourself, get the data, and then you can easily see it on your mobile in like 5 seconds. So that's where the biomedical industry is heading over. You have data science. So almost everything is moving to IoT right now, Internet of Things. So everyone is connected, every device is connected, all the data is stored in cloud right now. So that requires heavy computational capability. There also hardware comes in. So that is also built on the semiconductor hardware. You have artificial intelligence applications. So that's one of the videos that I showed right now, where artificial intelligence uses or leverages hardware to create amazing things in society. Then you have logistics, and then even you have automotive. So I am currently working in the automotive industry. I'm working on self-driving cars right now. So everywhere, everything that you see around, right? Your watch, your mobile, your even your TV remote has a processor inside, and every processor comes through VLSI design. So the breadth of the industry is very high, and it's almost like the IT industry during the dot-com bubble right now. Like the demand for VLSI engineers are on the high side. So talking about or giving you an overall uh, picture about how a VLSI design flow look like. So this is required for you to understand like where would you fit in. So uh, it all starts from system specification. So someone might be sitting somewhere and telling like, I need a 12 core CPU, or I need a 8 core CPU. I need this frequency. I need this clock. So that's where the system specification comes into picture. And then there'll be someone else sitting there and designing the architecture. So there is this AMD Ryzen architecture. Someone has designed, telling this is going to be my CPU architecture. Then someone else would be designing a GPU architecture. So that's basically the architectural design point of view. And then someone has to sit and verify it. Designing is easy, but it has to work, right? So someone has to put it into practice and tell, hey, this is going to work. And then comes the main part, that is logic design. So till now it's all conceptual and specifications. Right now you're actually going to implement it at the digital logic level, and then someone has to verify that logic. So all of this is what you call as front-end design in VLSI. So everything till here is what you call as front-end design. So VLSI has two streams. There's a front-end design and back-end design. So after that, all the logics that you've created, for example, your chip might have a camera, your chip might have Bluetooth, your chip might have USB. So logic design teams will be creating multiple of them. And then someone has to put it together into a chip, right? So that's called circuit design. Someone has to verify the circuit, and that's called circuit verification. And then comes one of the most crucial elements of a chip, that's called physical design. Till now you created circuit on maybe a software, maybe you have it on paper, but then ultimately what happens is like it has to come out as a chip, right? It has to come out as a die, which is manufactured, which is made out of metal, which has different doping. You create some semiconductor. So ultimately it is going to have only some PNP transistors and then some wires and some metals, right? So physical design actually does that. Physical design converts a digital circuit into actual physical components in terms of metals, capacitance, and everything like that. And someone has to do the physical verification, make sure that everything works. and then we call it tape out. At that time, what you release is something like a snapshot or a file which has all the specifications, measurements, and then you give it out to the manufacturing people. They manufacture, and then you get out a chip in hand. This is what how an overall VLSI design flow will look like. So, what are the different graduate job roles we have in the VLSI industry, right? So, not all areas is something that is accessible to a person who is going to graduate and then get into VLSI. So, you might have access to logic design. You might have access to, as I mentioned before, logic designing, digital design, or analog, up to you or up to the openings that we have. And then we'll have design verification openings. People have to, so most of the project, right? If you consider project an actual industrial project, about 40% is design and 60% is verification. So someone would be sitting and designing something, but then someone else has to sit and also do everything to make sure that it works. And then there is DFT. I'll be talking about DFT later. That's called design for testability. Once it is manufactured, you have a die, right? You have a simple die or a chip in hand. How do you know that it's going to work, right? You cannot simply gamble, put it into a mobile or a laptop and then say, hey, it might work, it might not. You cannot ship it to a customer like that, right? That's where DFT comes into place. So I'll be talking about that a little later. And then there's physical design, as I mentioned, placing the actual design in physical world, placing them, routing them, creating metal layers, and all of that, and final tape out. And then you have an area called post-silicon validation. So that happens when DFT make sure that the chip is actually working, and then it hands it over to the post silicon validation team, and what they will do is basically after fabrication they'll be verifying the features. For example, your chip might have a function to enable IR camera. Your chip might have a USB 3.0 or USB-C. So what post-silicon validation team would be doing is like they'll bring up the software required for all of this, and then they'll connect. They'll make sure that the USB is working. They'll make sure that Bluetooth is working. It's up to the specifications. It's what we intended. So these are the general areas in which a normal graduate can get into. Under this itself, there'll be multiple streams, but this is a broad classification. So now comes the important point, right? So it's not, there is no one point of or one golden rule of knowledge like software, right? So if you want to get into the software field, you have to study programming, you have to study data structures and algorithms, you have to study object-oriented programming, computer architecture, things like that. But when it comes to semiconductor, it's spread across. So you need a lot of theoretical knowledge and application as well. Softwares, yes. So it's spread across multiple areas. So what emphasis you have to give? So in terms of software, you might say you have to give more emphasis to coding, right? It might not be the case in hardware. In hardware, emphasis might have to be given in design more than programming or coding. So I will just touch brief on each of what you need to get into this industry. One more thing I want to tell you guys is like, you cannot, it takes time. So you cannot make it in a week or so. Heck, you cannot even make it in a month, okay? So it takes more than that, because the amount of things that you need to understand and your brain has to absorb is very, very huge. So you have to know that, you have to plan for it, and then you have to keep time aside to actually, if you are looking at this seriously, then you have to put in serious manners to get the job done. And also it's very hard to fake a VLSI interview. In most of the other interviews, maybe you can go by, you could say, the usual things that all of us might say for interviews, I'm a quick learner, I'm a team player. They don't care about any of those. All they care is whether you know this, you don't know, okay, we don't want you. So yeah, you would have to know the digital design fundamentals. I will go over these in detail after this. You will have to know advanced digital electronics, both combinational and sequential logic designs. You will have to know, so everything that you studied, I guess most of the students are electronic students here. So mostly in our, at least in Kerala undergrad curriculum, we might be studying 90% is BJT, that is PNP normal transistors. So those are like 40 years ago tech. That's not used in the industry right now. BJT is obsolete. So everything runs on, even MOSFET is getting old right now. Everything runs on FinFET right now. So companies expect you to be aware of the current tech. They don't care whether your syllabus had it or your syllabus didn't have it, whether you studied in your college or not. If you're gonna go into the industry, they expect you to know something in advance. And one of the things is MOSFETs. Everything runs on MOSFET, so you'll have to know the basics of device physics of MOSFET and the digital design using MOSFET. And then comes the implementation of it. In industry, all of the logic is implemented in a high level language called hardware descriptive language. That is, one of them is Verilog. This is similar to C. So in software world, we have problem statements which we solve using code. So similarly, in the hardware world, we have hardware design statements which we what can I say, which we implement using Verilog. And then you need to know what is the basics of ASIC design. So you don't have to know in depth and all if you are an undergrad, but then you will have to know what are the different components or areas of ASIC design, and then you will have to know what DFT is. Uh, I'll be talking about that. Then you will have to know what timing analysis is. So timing analysis is one of the most important things in VLSI interviews, industry, design. Overall, it's one of the most crucial elements. And then you'll have to know some basic programming as well, because you'll need some sort of programming or computer architecture understanding here and there. So digital design fundamentals, right? So most of you might be EC undergrads. Even if you're not, it doesn't matter. I was a triple undergrad. So you would have to start from the absolute basics. So right from logic gates, normal digital number systems, K-map, how to create a normal circuit using small gates. You start from there, and then you go to something very advanced, like creating circuits using combinational elements, going to things like sequential elements like flip-flops, registers, counters, and then you have to go into circuit design using all of these. So this is the absolute base of VLSI. So even if you take months to understand these things, it's worth it, because everything that you're going to learn or everything that you're going to apply in VLSI would be based on this. So if you ask me where to prepare all of these things from, I personally refer the lectures from NPTEL, Prof. S. Srinivasan, IIT Madras. So in my opinion, NPTEL has one of the best material for VLSI, at least in India. So I've attended even MIT free lectures online as well, but the IT ones were even better than them. So we have the content available for free in the internet. So it's just about how much effort you put in to understand these things. I think the digital design lectures are like 40 hours in total. So that 40 hours will take you from the absolute basic, right from an AND gate maybe, to creating a very complex computer system as well. So it's worth it. So that's what I used personally. It's very a little hard for me to focus on books, so I prefer that. If you prefer books, you have the Morris Mano. That's the golden standard of digital design in the industry. Even industry folks use only that. Uh, it might be difficult to understand. The NPTEL lectures are, it's very simple language that it's easy to grasp. Then if you go to basics of MOSFET, right? So everything, as I said, in VLSI is made of MOSFETs, CMOS circuits. So you will have to know what is the internal structure of it, how it works, what is its characteristics, what affects its performance, how do you design circuits using them. So it's only up to this level you have to know. Beyond that, you don't have to know, at least from an undergrad perspective. So for postgrads, you might need even higher, but then I'm not going to talk about that. So Uh, I personally referred CMOS. There's a book called CMOS VLSI Design by Neil Veste. I'll share the PPT after this. Probably you can take a look at that later. So this book, I don't know whether our college libraries might have it. I think you can download online. You'll be having PDF versions available. That's what we use at least. We didn't have textbooks back then. So uh, MOSFET is very important. So in interviews, you might get a lot of questions like, what if I keep my PC in Alaska, where the temperature is like close to 0 degrees Celsius? What will happen to my computer? What will be the performance? Then you have to understand how the device physics works, how temperature affects the electronic components. So all those things to understand, you'll have to know the technical aspects of it. So that is where this device physics of MOSFET comes into picture. Then comes Verilog. So everything till now, you would be basically creating circuits. You will be stitching together circuits, drawing circuits, creating flip flops, counters, adders, multipliers, things like that, right? So that's on paper. So how do you basically get it into a chip, right? How do you create logic or circuits out of it? So that medium is what you call as Verilog. So like C programming, it's a very high level programming language. I don't know how many of you guys know about this. So this is starting point to get into VLSI. You need to know this language. You need to know how to code in this. So you have to know uh, what are the different Verilog constructs. So like C programming, what is the syntax, uh, how to create a Verilog function and things like that. How do you code logic gates? How do you code flip flops? All of them have different styles of coding. How do you create case statement based coding for functional state machines? Things like that. So essentially, whatever you so even your undergrad curriculum, you'll be creating circuits and counters and things like that, right? So how do you basically create hardware out of it is what Verilog will be doing. So I personally referred to a book by he's an industry guy called Samir Palnetkar. The book is very very good. It's written in like easiest language possible. Anyone who doesn't even know excuse me, anyone who doesn't know uh, uh, even digital electronics properly might even understand this. So it's a breeze to read through, and also I preferred this more than lectures. So whatever I'm telling right now, like I would have experimented multiple things. I would have experimented videos. I would have experimented Coursera, Udemy courses. I would have experimented foreign authors. I would have experimented Indian authors. So whatever I'm telling you guys is like what worked. So that you guys don't spend the time experimenting for things, right? So you would be having your undergrad curriculum going on parallelly, or you would be graduating and you will be on the search for a job hunt, and at that time you don't have time to experiment, right? So whatever I'm telling is stuff that I'm pretty sure that it works. And then comes DFT. So as I said, you manufacture a chip, you get a chip out, you have a die in your hand. There is no way of knowing that it works or not, right? So suppose I design a chip, I design a chip for a self-driving car, suppose. I take, or my team or my company takes 3 years to design it. It got manufactured, it came to you, and then you started powering up. It's not working. What do? There's hundreds of millions of dollars you've already put into design and manufacturing, and then you don't know why it's not working, right? Because ultimately what you have is a piece of metal. What you have in your hand is a piece of metal in which some wires or things are going here and there. So how do you know what is going wrong? So that's where DFT comes into picture. DFT stands for design for testability. So what DFT does is create extra logic in the chip to make sure that you can test each and every point in the chip. For example, uh, your chip is not powering up. You might want to check whether it's a problem with your memory. If you have DFT methodology in your chip, you can dump out each bit in your memory to see where it's going wrong. You can check if it's a problem with the IOs. You can check if it's a problem with core logic. You can identify all types of faults in your chip. So that's equally important because uh, when a chip is manufactured, right, you might think like every chip is going to work. That's wrong. So in the actual world, if you manufacture chips, the average yield is around 40 to 50%. That means only 40 to 50% of the chips work as you intended. 60% of it don't. And if you're not going to test it properly, then you might be giving 60% chips which is not going to perform as you promised, right? And that's going to be a disaster for the company. So that is where DFT comes into picture. So DFT does multiple things. One of that is analyze faults. Second thing is basically binning, something you call as binning. So what binning is like, you might be having, you might have heard of like i9 processor, i7 processor, i5 processor, things like that, right? So i9 will be the most powerful, i7 will be the second most powerful, i5 the next, like that. So after manufacturing, so suppose I'm manufacturing 1,000 i9 chips, and then I found out that out of that there are about 300 chips which are not working as intended as an i9 chip, but they're still okay. But you might be expecting 2.4 gigahertz clock or frequency. You're getting 2 gigahertz. So what you'll do is like a DFT will be having extra logic in place. It might shut down some cores and release it as a 5-core CPU. That means the chips which were not working as intended now is going to be shipped as an i5 processor. So you're not wasting any money. So even the bad chips or the chips which are not working as much as an i9 is still going to be sold as an i5. So basically you are trying to make the most out of the money. So you're trying to make the most out of the chips that are manufactured. That's what happens in the industry right now. You might see an Nvidia GPU to 2080. You might see an Nvidia GPU 2070 or 2060. 2060 might be actually a 2080, which did not perform as much as 2080, and then decided to sell it as 2060. So that's what we call as bending. So that will happen only if you have DFT architecture in the chip. You are able to measure frequencies. You are able to measure the performance. You are able to understand the faults and things like that. So from from a preparation perspective, you will have to know what are the different types of faults that can happen in a chip. There are different types of faults. So you will have material. When I say about the material, you can check that. What are the different patterns you can generate to identify the faults? So certain faults can be identified using certain patterns that you give into the chip. So what are the kind of patterns you can give? How do you, there's something called as boundary scan. That's a DFT standard. So there are things like built-in self-testing, LFSR. These are actual logic circuits which help in identifying faults. So to learn DFT, I would personally prefer the VLSI Physical Design course by Prof. Indranil Sengupta, IIT Kharagpur. So that's a very big lecture series. Okay, you don't have to learn the whole thing. So that's I think that's 40 50 lectures. In that itself there's a subdivision for DFT. I think that it's around 4 or 5 lectures only. In that he gives a very good understanding about what DFT is and the different items which I mentioned. That would be good enough for your purpose. So everything else you will learn once you get into the industry. Next thing is basics of the ASIC design flow. So you will have to know what are the different stages of ASIC design. So like what I said, the VLSI design flow I explained, right? What are the different components? So there are different components or stages in the ASIC design as well. You will have to know a brief idea about all those things, these things, and then you will also have to know what are the different types of models that we use for ASIC design, things like that. So you can either refer that guy's Prof. Indranil Sengupta's lectures, or you have a book as well, Michael J. Smith. So that's pretty good book. So this also you don't have to know in like very in depth from an undergrad perspective. You can just touch base and just have an overall idea. That would do. Next is timing analysis. So timing analysis is something that you need to know very in depth. So to explain the significance of it, right? So suppose you have a chip and the company says its frequency is going to be 5.4 gigahertz or 5 gigahertz, right? How do you ensure during design that it's going to be 5 gigahertz? So that's where timing analysis comes into picture. So timing analysis takes each path within a chip. It takes each from a point A to point B. It checks whether it's going to meet the frequency. It's going to meet the speed that your chip is going to that your chip demands or what you promised. So that is what timing analysis does. So there are certain timing standards or terminologies that you have to understand, like setup and hold violations. How do you fix issues? How do you calculate the different parameters? How do you calculate given a circuit? This is one of the most common VLSI interview questions ever. Like they'll just throw a circuit at you. They will just draw a circuit and give it to you. They'll give some parameters and they'll ask you what calculate the maximum frequency at which this circuit can work, or calculate or tell me how fast this circuit can work. So for that, or for to understand that, or to analyze and solve it, you would need to know the concepts of timing analysis. So timing analysis from top to bottom is explained in a website called VLSI Expert. In that, there's a particular section called STA. It's very easy to understand from that particular place. Otherwise, if you go for books and all, it gets very complicated. So you will have to learn that very in depth. So most of the questions in VLSI interviews and in the industry as well, this is very useful. So mostly on a day-to-day basis, you will need to have a good idea about this. Next is C programming. So C programming, I would say it's not an absolute must. It's good to have. So most of the companies during its what do you call elimination, right? To eliminate people, they might have some C programmings here and there. So they would have some some snippet of code to find the output, or give you a problem statement to code or things like that. So it's good to understand and know programming. And I would so companies still during interviews prefer C, but most of the industry work happens in Python, Perl, or Tickle. So but all those things you can learn once you get into the industry. But before you get in, I think one language is good enough. So data structures is also needed. So understanding of data structures, I would not say learn to code complex data structure problems and things like that. I would say understand each type of data structure, how it works, how do you access each data structure, how is data interpreted in a data structure, things like that. So you can learn from anywhere. So programming, I don't have to give you a guideline, right? So there'll be hundreds and hundreds of tutorials, hundreds and hundreds of books. So I personally referred only one YouTube channel, My Code School. It was very simple, 5-6 minute lectures, quite a lot of lectures actually, 150, 160 or something. But then it was like 5 or 6 minutes. So my attention span, it required only small time. So it was fine. So I guess so now you would have actually got somewhat of an idea about what all things you need to learn, right? So this is a very vast syllabus. I cannot say it exactly a syllabus. It's a very vast amount of information that you have to process. So in my case, I would say I took 6 months, about 6 months. I was from triple E background, so to give an idea, honestly, I didn't have any idea about any of the things in electronics much. So I had to start from scratch. I think it took me an easy 6 months, 6 months of maybe 4 to 5 hours prep every day, and last 2 months maybe 10 hours, around 10 hours. So that's what I took to get into Nvidia. So it's gonna be in the similar lines if you have to get into any major country. So any major company, sorry. So so that's what about the technical aspects of it. If so, talking about different types of circuits or designs, how do you approach problems, right? So interviews is not going to be like your exams, right, where they're going to ask you, design a 2-bit subtractor, or design a 4-bit multiplier, or design uh, a divisible by 3 circuit. No. So interviews are going to be very tricky. So they're going to give you scenarios, like they're going to give you a scenario like design a circuit which determines if design a circuit whose inputs are zeros and ones continuously coming in, and if two zeros come in together, your circuit identifies it. So how do you design such a circuit? Or they might ask you to design things like a traffic light in a 4T junction, where you have a T junction and you have traffic lights kept on all 4 sides. How do you design an electronic circuit to handle that? So things like that. So it's not gonna be straightforward. So you have to understand how to solve such problems, and that takes practice. So I would say, so in our times, we had something. So this is something like a question bank that we ourselves in Trichy created. So it is like a accumulation of top questions or type of questions from almost all big VLSI companies. So it would touch base on every type of topic, and also uh, it would it would actually be targeting on very conceptual problems. So this is what we consider as a Bible or Quran of VLSI interviews in Trichy. So after you know your theory, after you know how to design things, if you're able to solve this particular question bank, or whatever you want to call this, then that means you're almost ready to attend interviews. So I will share this along with my PPT to the coordinator of this presentation. So this one takes time. So you would not be able to solve these questions at first. So it has solutions as well. So I would request not to look at the solutions at all in the beginning. So in my case, even if it took 2 days to solve a question, 2 or 3 days to solve a single question, I never looked at the solution. So I would just sit and think about it. If I got the answer, no, I would think again. I would go and ask someone who I think would probably know the answer. He might give me some inputs. Even then I would not look at the answer, because at that time you will lose the thought process. You will already know that, oh, this is the approach that I have to take. So you should not be doing that. You should be creating your own approaches. So You will be able to do that over time. So once you do that, and if you're able to solve this set of questions, this is like curated set. Not one question is repetitive or repetitive or is of the same type. Everything will be of different type. So it will give you a very good combination of different types of design problems that industries ask when they come for interviews. um, with respect to projects, I would say focus only on front end design. So front end design means, for example, so let me go back. I would say focus on only projects which focus on the left side of this, right? So you will have your problem statement for your project. You will decide on the architecture that you want to use. You will do a brief verification of the architecture. You will design the architecture. You will code it in Verilog. You will synthesize it, and you will be verifying it. So I would say, if you want to create a portfolio for VLSI companies, only do till here, because everything else is very deep, and that requires many a very good technical knowledge, a formal technical knowledge, which we can not acquire through internet. And the tools also, you will not get access to any of these tools on backend design. Front end design, at least you can get cracked versions on internet. I'll tell you which softwares to use after this. But then backend design, no way, because backend design, the physical design tool alone would cost you like 40-50 lakhs, just the software. So that's those are things that we won't be having access to, and we don't have to also, because those are things that you will learn if you get in the industry. Before that, I would say only focus on the left portion of this. Uh, for example, uh, so if I want to talk about what I did for masters for my project, right? So I did two projects. So one was uh, to create an artificial neural network. That's an AI network to detect a tumor in kidneys from CT scan, and also to grade the level of tumor. For example, I go and take a scan from any med scan normal lab. I take CT scan, I take a digital image of it. You give it to my network, and then it will tell whether you have kidney cancer. If you have a cancer, it will also tell what is the stage of cancer you're at. Something similar to what you saw in that video. So, so that's something I did for my uh, first level of project. So the second project was to create a hardware circuit of that. So what I did was, like, I created proof of concept. I created models of this. I modeled this in MATLAB. I trained my network, gave it input parameters, made sure it worked perfectly. And then what I did was to create the hardware for this. So in my case, so uh, when you approach every problem, right, you need to have a problem statement. For example, this is a kind of problem that I'm going to solve in my project. And then once you have that, uh, this is what makes it different from the rest of it. So uh, you cannot go and create artificial neural networks simply, right? There are hundreds of artificial neural networks out there in the market. So all the hardware will be already created. So what is different in your project? That is very important. So in my case, I created a low cost, low area, low power consuming circuit. So so you need to have that, what you call as novelty in your project when you create a project. So even the interviewers will be asking that, what makes it different? So he might ask you, like, this is something that's already there. Why do you even make it again? Something like that. So you have to identify such novelty and then focus on that. So in my case, what I did was, like, you had normal circuits. So I would say this is like what normal neural network would look like. So you have inputs, you multiply it, you get the weights, you propagate it to next level, propagate it to next level. This is what a general artificial neural network or an AI network, feed forward neural network would look like. So this is what the conventional circuit was. And then this is what a conventional, the single circular thing, this is what the internals of it would look like. It would have a multiplier, it would have an adder, it would have a summing function, it would have an activating function. This is how it would look like in normal scenario. Then I replace it with some other circuit. So I use some methodology to create another circuit that would make it consume less power and would consume less area. So less power means more energy efficient. Less area means you save cost in terms of die size. So then when you go ahead and implement it, so you write the Verilog code for it. So here, if you see, I have a counter, so I go and write my counter code. So you'll have to learn how to code in Verilog. So you can refer to that book I mentioned. So you have to learn how to code, and then you can go and code each and every component in this. So it's simply like C function, C programming. You'll be creating your own functions, right? Similar to that, you'll be creating activating function. You'll be creating counter logic. You'll be creating adder. You'll be creating different things, and then finally you will create a single circuit which would be including all of this. So I created my circuits on the software, and then after that I simulated my circuit, and then I gave inputs and then saw whether my outputs are expected. So in Verilog, the software that is, I will be talking about the software after this. So you can give inputs and see outputs and see whether it's working as intended or things like that. So that helps in functional verification as well. So also using the software, you can see how much area your circuit consumed, how much power it consumed, and based on that you can actually compare it with the existing architectures and things like that. So that would make, so in my case, the extreme right, whatever is there, that was my architecture. So it consumed less, it had less delay, it consumed less area, it consumed less power. So that made my circuit better than the ones that are already there in the market. So for the software, so the software is what you call as Xilinx ISC. So you will have tutorials on how to use the software in YouTube. So the software is a paid software. You will have cracked versions online. Uh, I don't know any free versions of Verilog simulators available. It might be available, but I don't know how to get them. So in our postgrad, we had access to the license, so we didn't have to use the cracked ones. But I checked YouTube today, and I was able to find the installation and APKs for this directly in YouTube. So that would not be a problem, I guess. So in this case, so I am preferring cracked options only because you guys as students, you cannot afford these things. But then once you get into industry and all, you are not allowed to use it. That's one of the reasons why I have not installed this in my computer. This is my work laptop. So if I install, it would be violating the company regulations. So because of that, I've actually created a document that we used, which would actually walk you through each step in the project and things like that. So that would make you guys easier to understand. So I would share this document as well as a part of this. So this software you can download. So the advantage of this software is like you can go and create your own. It's similar to writing a C program, right? You can create your own code, and then once you create, you can create your own project. You can create, select what type of chip you want to choose. What is the type of what do you say? What is the language you want to code in? So in this case, you want to code in HDL. Then you can see like what I want to create, whether I want to create a Verilog or VHDL or something like that. In your case, the language is going to be Verilog. You create your own project, and then you tell what is going to be my inputs, outputs. To understand this, you will have to know how to code in Verilog. So I'm not going to go in depth. So then you can go and write your code like this. So you can write your code. Once you written your code, similar to any other compiler. This is like a OR gate that they've written. So you can uh, once you've written your code, you will be also be able to see what is the circuit representation of your code in parallel. You can see. So this was an OR gate, so you're able to see an OR gate representation, and then you can write test bench. Test bench means you can write inputs and see what the output is going to be of your circuit. Then you can write that, and then you can actually see what the output of your circuit is. So you give inputs, you're getting output waveforms, and you see whether it's going to be expected as or not. So all of this you can do in in the software. You can do more also, like you can also uh, there's something called synthesis. So what synthesis does is like now you create your logic, and it will load that logic into some dummy hardware. Dummy hardware will be things like things what you call as prototyping boards. So in electronics you have things something called prototype boards. These boards will be empty chips. So based on what you load in them, it will create new hardware logic. That's the simplest way in which I can explain. So you will be having dummy boards with chips which doesn't have much things in it. After you create your Verilog, after you create your design, you can load it into that board, and then that board will actually be the circuit which you designed. In your case, you won't be having access to board and all, so you can do the things just before that, till that. So you can create your design, you can create your Verilog, you can simulate it, you can see whether it's working as expected, and then once you have that, then you can create the synthesis of it, and then you can see how much area it's consuming, how much power it's consuming, things like that. So so when I check today, you can find even tutorials online on how to use this. So YouTube has, so this is what the software, Xilinx ISC is a software. Uh, YouTube has a walkthrough on how to use it, how to code, how to simulate everything. So it's everything is available. So once you learn Verilog, so you cannot go and directly learn to code, right? You have to learn whatever I've told. You have to learn digital design. You have to learn Verilog, and after that you can start programming. So one of the advices what I can give while you start with projects is that start from small projects, like start from simple circuits like adders, subtractors, multipliers, code, and get yourself familiar with how to code, what are the different types of errors you can make, and then once all of that is done, then you can take bigger problem statements and create circuits. For example, you can simply go through IEEE and then just type in some VLSI design, and then you'll get many papers. So those papers won't be having codes, right? The papers will only be having problem statement and solutions. So what you can do is maybe is like you can create your own Verilog design for it, and then try to simulate and see whether it's going to work and things like that. So uh, that would make you actually very familiar with how to code in Verilog and how to create circuits using Verilog design. So, so let's assume that you've learned everything. So let's assume that you have learned whatever you need to, whatever I've told right now. Even that is not like 100% complete. So you can still learn things beyond that. You can keep on learning, but then this would be the absolute baseline of things that you need to understand if you get into a VLSI industry. So even if you have that, how do you basically get into a particular industry, right? So you will have to find options to get in. So one of the options is campus placement upon graduation. So if your college, whoever is listening, you might be from different colleges. So if your college has campus placements for VLSI, well and good. You talk to your seniors about what are the kind of companies that are going to come. You start preparing whatever that was mentioned in this presentation. You can start preparing early on. So it's going to be, the syllabus is going to be absolute same for almost all companies. And you can try and crack it through your undergrad placements. So if you're not able to, right? So in my case, I in our year, yes, we had many VLSI companies, but I think I didn't even know when they came to campus, I guess, because I was actually not paying attention to placements at that time. And also I was from Tripoli and I didn't have access to most of the campus placement companies. So if you are in such a situation, right, if you are in a situation where your college either doesn't have VLSI companies coming in, or you're not eligible or you're not able to make it, then the option is going for a postgrad. So postgrad, there are two options. You can do an MS abroad or you can do MTech in VLSI through GATE. So I would say it's a personal choice because uh, if you do an MTech in VLSI in a very good college, that would be enough. You would still get a very good job in India. If you do MS abroad, that would all, you would have to do it in US. Doing it anywhere else would not guarantee you a VLSI job. Doing it in US probably will, because most of the semiconductor giants are in US. So it is a personal choice, like how much of an economic risk you want to take. Like, are you willing to take such a big loan and go and study there, or are you okay in moving out of the country? So I was not okay with both of them. That's why I chose the MTech route. So even I don't find much of a difference. Even if you do masters in India, if you're doing it in a very good college, it should be good enough. You'll get a very good company. Just that, you'll be working here, so even work will be very nice. So it's not like you're working in US, the work is going to be better than the work in India. Nothing like that. In VLSI industry, if you're going to work in a very good company, you would be doing quality work here in India as well. And I personally would say that getting MTech in India is harder than doing MS abroad. Uh, in the sense that getting an admission is harder for an MTech in a good college than an MS in US, because MS goes through GRE, MTech goes through GATE. GATE is very tough compared to GRE. I've tried both. I would say GATE is much easier, much tougher, because technical aspects of it would be, syllabus is like very huge, and then so that's another thing you have to focus on, like whether you want to drop a year and study for GATE, or whether you want to uh, study GATE, crack it parallelly, or you're okay with learning aptitude, language, and things like that, and cracking GRE and then going abroad. So that's a personal choice. So another thing is like doing internships, right? So this is something that we didn't have access back in 2013 or 14 when we were in college. So we didn't have access to LinkedIn and all back then. I didn't even know, I think LinkedIn existed when I was in my undergrad until final year maybe. So basically you guys have more access to internet and more access to opportunities. So I would say try to find internships and all in VLSI companies. It doesn't matter which company, right? You don't have to go and do internships in like very good companies. You can do it in even small companies. It doesn't matter. You will learn a lot. You might also get an offer after completion. Some colleges have, like, you might be doing your final year project in a VLSI company and things like that. I know BITS Pilani for BTech has it. Even I think most of the colleges outside Kerala has it. I don't know whether KTU has the provision to do that. Back in our time, we didn't have such provisions. We were forced to do projects in college itself. So you can try out. So for people who are like in final year right now, I would say you can look for opportunities for internships in companies through LinkedIn and all. For students in second, third year, I would say you can you can start exploring LinkedIn, get create a very good connection network, see for internships, try getting in an internship as early as third year or second year summer, and then get yourself used to the industry, and then that way you can actually land an interview and a job. The final way I think you can get in is through VLSI training institutes, right? So so there is Bangalore is like the hub of VLSI training institute. Bangalore and now Noida is also there. So there are like 6, 7 prominent VLSI training institutes which give PG diploma courses in like 6 months, maybe a year. Some do 1 year course, some do 6 months course. So there are different institutes. So if you perform well there, you would be having you would be getting interviews with companies associated with those institutes. So most of them will be services companies. It will not be a product company. So something what means like a service company is in the sense that, suppose let's say Qualcomm makes a chip, right? So Qualcomm makes 865 chip. So it has camera, it has USB, it has modem. Services company means that company might be making modem, uh, a modem for Qualcomm, or that company might be making USB for Qualcomm. So it is not releasing a product of its own, but it's making product for putting in some other company's end product. So it doesn't mean that you're not going to do good work. You're going to be doing very good work. Uh, but I would say uh, opportunities are more in services company right now than product companies. So this is one of the ways in getting in. But you can always walk your way up from a service company as well, because I had a colleague of my I have a colleague currently who's working in Nvidia. He did his course in a VLSI training institute in Bangalore, worked in services company for a couple of years, and then jumped into Nvidia to with his experience and with an off-campus interview. So that is also possible. So it's not like if you go into a services company, you're going to be stuck there. So if you work hard, you can even uh, get a good product company job from there as well. So if you guys want to reach me, you can reach me on LinkedIn. You can email, or if you want to connect with me on WhatsApp, you can ping me on WhatsApp. You can shoot any questions if you have. So after this, I can share uh, the two PDFs I showed. One is of the question bank, if you want to call it, and the second is of the software tutorial that you can use to start on how to code in Verilog and things like that.
That was a great session, Akhil. Thank you for being with us here. If anyone has any questions, you may ask them now. Also, the form for availing certificates is in the chat in case you missed it.
Okay, so someone asked whether model sim is enough. So model sim is enough. So model sim would help you in simulation. So model sim is, for people who don't know, it's also not open source, I get, but you can get student version. Uh, in that also you can code in Verilog, simulate and see things. Difference between the Xilinx ISC, which I showed, and model sim is like Xilinx would load this into hardware and show you how much area you're going to consume, how much logic you are using, and then that would make you understand like whether your circuit is efficient, or if your circuit is consuming more area, you have chances of improvement and things like that. Uh, Second question I saw is Python enough? With respect to Verilog, Verilog is absolutely necessary. You don't have a substitute for Verilog. You need to know that. So Python is something which you can use once you get into industry. But then that is something you can learn once you get in. To get in, I don't think you would need that. Second question, and the next question is like embedded systems and VLSI തമ്മിലുള്ള വ്യത്യാസം എന്താ? Okay, so embedded system is something like you have a processor. For example, you'll be using some microprocessor, let's say 8085 or Arduino and a processor in the. So you take that processor, then you will be coding in some embedded C, something like that. Then you'll be loading software and then using that for some application. So the processor is already there, right? So we've already created processor. So in VLSI, that is something where you are actually creating that processor. So you're creating 8085. You're going to create the internal circuit of 8085. You're going to design it, and then you code it. You're going to simulate it. Second, next question is like, what kind of projects will help? I would say digital circuit based projects. So some things like efficient multipliers, efficient adders. You can find hundreds of examples online. So things, you can just Google it and you can get hundreds of ideas, and then those ideas you can develop on your own, because there will be open research papers available in IEEE and all. You can implement it in design on your own. I would say focus on projects which I would say take IEEE papers and implement that using Verilog. That would be the best way to do things. Next question is difference between Vivado and ISC. Vivado is one company's software, ISC is another company's software. Vivado is one level higher than ISC. So Vivado can do much more things than simple synthesis. It can do even placement routing and things like that. If you have access to Vivado, then okay, well and good, you can use that. Otherwise, ISC would be perfectly fine to start with. VSDL instead of Verilog. So for people who don't know that, we have multiple languages. We have VHDL, we have Verilog, we have system Verilog. So I would say Verilog. VHDL is very old. So VHDL came first, and then Verilog, and then advances of Verilog, and then system Verilog. So VHDL is quite old. None of the industries use it, as far as I know. So it would be at least best to learn something which is at least partially used. Verilog is somewhat used in most of the applications. So learn something which is relevant right now rather than something which is old. What are the applications of ML and DL in any of the VLSI design flow? Okay. So there's a certain category of engineers called CAD engineers. So computer aided design. So what they do is like they develop tools to using ML and DL to make work easier for design folks. For example, I work on an autonomous chip right now, a self-driving car. So in that case, I want to design something. I cannot use softwares from outside. We will be creating our own software. So it is this CAD engineers who will be sitting there. We will be giving them what kind of software I want to use, and then they'll go and code it, and then it will be very efficient things like they'll be using ML and DL in many aspects to make our work easier. One of the things I can say is like in terms of placement and routing. For example, you have a chip, you have point A to point B. It's a path, and you want to connect those two circuits. You can take hundreds of paths, right? So if you use ML and DL that the tools use, it will show you what is the shortest path you can take, and then you can directly choose that instead of manually reviewing things and things like that. Linux-based developer tools. Linux-based developer tools for Verilog, I don't think so. Linux-based tools, once you get into the industry, yes, you can have many Linux-based developer tools, but you don't need them when you are learning. I don't think Linux tools are there. It is there for placement, routing, physical design, and all. I don't think you would need them right now. When you start out for undergrad or placements, I don't think you would need Linux developer tools. That's more into software side. And software side, I'm not talking about it right now here because I'm not a software guy. So there are Linux-based drivers, Linux-based SDKs, things like that. That is for the software engineers, not for the hardware engineer. Is it better to get placed in VLSI now or after pursuing MTech? Okay, I didn't have an option. That's why I pursued MTech. If your college actually has opportunities, right? It's better to get placed right now and then in your company. So because uh, basically you are losing time, right? So you're losing 2 years. If you're interested in getting a degree, that's well and good. But if you have an option to get placed now in the industry, to be honest, an extra degree doesn't matter. So no one cares if you have an MTech and because of that you will get a better placement, or because of that you will get a better role or better salary and things like that. I don't think that's going to happen. It's just that MTechs have higher preference in terms of placements when you're doing MTech, but then because of that, you don't have to basically not join a company if you have a chance after graduation. Okay. Then what kind of projects are expected by companies like Nvidia? So Nvidia mostly don't focus on, as far as I know, they don't focus much on projects, to be honest. So they'll be, as I said, they'll be focusing more on technical knowledge. So they'll be putting questions to your left and right, and then asking you to solve them, and, explain your approach, design problems, things like that. So for me personally, the project that I explained was not even completed when I was actually interviewing for NVIDIA. So it didn't matter much. Good training institutes. Good training institutes. I cannot recommend any because I've not gone to any of them. I would say there are many actually. I would say there is RV, there is Maven Silicon, there is RV Training Institute. There are many in Bangalore. And most of these have association with one company or the other. So you will get. So my friend studied in Maven Silicon. He got into L&T. L&T also does VLSI. He studied there. He studied in Maven Silicon for a year. Got into Maven Silicon. Then went to L&T for 3 years and then to Nvidia. Best colleges in India. So best colleges in India, I would say IIT Bombay, then IIT Madras, IIT Bombay, maybe IIT Kharagpur, then it's Trichy for VLSI. If you're talking strictly VLSI, fourth would be Trichy, because almost all the companies which go to the above three colleges would be coming to Trichy, NIT Trichy. Just that the companies from US and China or Japan won't be coming. How much did you know about all these things while doing BTech? Absolutely nothing. So that's the case, right? So I have done many things. So I did BTech. At that time, I had my own company that was not related to any of this. I was into stock market. I did that for a year and a half. Most of my colleagues got placed in very good companies like D, Shaw, Oracle, Zynga, and things like that. They dropped. I had to shut down my company, and then I went to Delhi for a year. I was there. I came back. I could not get into a PSU. Actually, I didn't want to get into PSU as well. And then later, I worked as a teacher. So I taught in these tuition centers. People who are in Kochi might know, Gurukulam. I taught in Gurukulam for a couple of months. I taught in Solutions for 4 months. I've done multiple things. So it's not like I knew any of these things. So it's only after I got into masters I knew about VLSI, but how to prepare and things like that only after getting into masters. I was head of placements for Trichy, so I I was able to interact with almost every company in India. So based on that, I was able to understand how what they need and what they are looking for and things like that. So what kind of embedded jobs are there in Nvidia? Embedded jobs are there, but I don't know about graduate openings for them because I've never focused on it. Embedded jobs are mostly into like drivers. So Linux drivers, almost all. So you have hardware, you create your chip, but it has to work on some of the software stack, right? So that software stack is mostly based on Linux drivers, and then on top of that, these things like the advanced Python and MINAL. So below that, in between, you will have Linux drivers. So you will have openings for embedded there. But embedded opportunities are more in companies which create microprocessors, like NXP. NXP in Bangalore has embedded openings. Texas Instruments has embedded openings. NI, National Instruments, has embedded openings. Companies which work on things like this. So a pure product processor-based company, something like Nvidia, Qualcomm, and things like that, AMD would have less openings for embedded. Prepared gate from I prepared from ADC Delhi. 1 year I was there. How old are you? I'm 26. So anything else? Contact I had shared in my PPT. I'll be sharing the PPT. I think you can check that. Verilog, system Verilog. I would say Verilog. System Verilog is mostly very application specific. So system Verilog is one step higher. So with system Verilog, system Verilog is the future, I can say. But then it is better to understand Verilog, be able to code well in Verilog, and then go into system Verilog, because system Verilog is basically an improvement on whatever shortcomings Verilog had. So only if you know Verilog well, you'll be able to understand system Verilog easily. Verilog യൂസ് ചെയ്ത് അനലോഗ് സർക്യൂട്ട്സ് ഡിസൈൻ ചെയ്യാൻ പറ്റുമോ? പറ്റില്ല. So analog, so I didn't talk about analog here, so I'll talk about that. So there is another areas like analog circuit design, right? So analog circuit design, if you have 100 VLSI engineers, number of openings for analog would be like 2 or 3. So it's very less. That's the reason why I didn't focus on it. It's a very niche area. So to design analog circuits, you would need proprietary tools, which I think would need license, something like Cadence Virtuoso or Cadence, some high-level softwares which would cost you good amount of money. I don't know whether you can have any open source softwares. I've never used them. Your gate score, Satyam Barna, I don't remember. It was 3 years ago, so I don't remember. It was okay to get into an editorial. That's all I can say. ASIC analog LA focus chain Allah. No, ASIC mostly focuses on digital. So almost 90% of the openings you have in India is going to be in digital. Analog circuits focus, companies do focus, companies like Qualcomm focuses on analog. You'll be having RF design, microwave design, antenna design, modem, you have MediaTek, which focuses on. MediaTek is a company which generates processors for like the budget-oriented phones. You could say the Realme, mid-level Realme, Oppo, and things like that would be having MediaTek processors. You might hear about Helio, things like that. That's that. So those companies would have analog openings, but I don't know how much openings they might have, right? So I talked about the ones which you have higher probability of getting into. Significance of RISC-V. So RISC-V is next gen architecture. It has its own significance, but I would say the companies which focuses on RISC-V is like very few in India. I can say maybe under 10 companies maybe focuses on RISC-V. It's a new architecture. So some companies don't find the need to move to RISC-V at least for the next 10 years. So I would say focus on something that is relevant right now. You have you have startups which focus on RISC-V. They want to create the next cutting edge technology. So if you want to get into companies like that, it's good to learn. Otherwise, no. Tell something about Nvidia ARM. We are not supposed to talk about acquisitions on public forums, so I cannot talk about that.
Yeah, I guess we can stop the Q&A now. We did receive quite a lot of Q&As.
Sure.
Yeah.
Hmm.
So yeah, participants, thank you for your enthusiastic participation in this webinar. We'll be sharing the recording of this as well on our YouTube channel, so you can refer this webinar once again. And Akhil, if you wish to say anything, like if you wish to share any other resources as such,
I can mail you guys. Maybe you can attach the link or something in the video you want to upload.
sure. Okay,
Sure,
sounds good.
that would be better. Yeah. Okay. Thank you, guys. I hope it
Okay.
was at least useful. Some useful. Yeah. You can get in touch with me. I have shared my LinkedIn ID or email ID in the presentation. So if you have any doubts, you can get in touch with me. Yeah.
Okay. Thanks a lot,
Okay.
Akhil, for your time. Thanks a lot.
Okay. Bye.
Bye.